Late on the night of April 25th, spilling into the early hours of April 26, 1986, at 1:23 a.m., Reactor Unit 4 at the Chernobyl nuclear power plant near Pripyat in the Ukrainian SSR sat under a cold, gilded sky as engineers prepared for a routine safety experiment. The Soviet nuclear program had produced the RBMK reactors, massive, graphite-moderated channel-type reactors that did not have the steel and concrete full containment shells used in most Western designs. That design carried deadly quirks, a positive void coefficient that made reactivity rise as coolant boiled, and control rods with graphite tips that could displace coolant and briefly spike power when inserted. The plant's culture prioritized production and schedules. Director Viktor Bryukhanov and Deputy Chief Engineer Anatoly Dyatlov were under political and scheduling pressure to run a turbine rundown safety test to see whether a turbine's inertia could keep the pumps running during a station blackout. The night shift, led by shift supervisor Alexander Akimov and control engineer Leonid Toptonov, followed an official test plan that had been delayed and then rushed. The sequence of actions, the reactor's design flaws, and a series of human errors came together. Dangerously low power levels, disabled safety systems, and an RBMK that could punish even brief mistakes. That exact moment, the location, the time, the people, and the experimental procedure set the stage for the cascade of technical and human failures that followed. Pripyat, a nearby town of about 49,000 people, slept unaware just 3 kilometers from Unit 4. The test sequence began as a bare, brass clock procedure. At about 1:00 a.m. on April 26, 1986, operators were to reduce Reactor 4's power, shut off the turbine's steam supply, and measure how long the turbine's inertia would keep the reactor coolant pumps running during a station blackout. To prepare, engineers lowered reactor power far below nominal, a decision that exposed the RBMK to xenon-135 buildup, the potent fission poison that accumulates when neutron flux falls and then suppresses reactivity as it decays. As power sank to a few dozen megawatts, the core became sluggish and unpredictable. Xenon poisoning throttled the reactor and the control room instruments reported a collapsing power level. Under that growing pressure, Leonid Toptonov, a young control engineer with limited RBMK experience, and shift supervisor Alexander Akimov began to withdraw control rods to recover output. Those withdrawals violated standing protocol. Regulations required dozens of rods to remain inserted to preserve a safety margin. Yet the crew left only a few, commonly reported as 6, actually engaged in the core. Anatoly Dyatlov, the stern deputy chief engineer who supervised the experiment, pushed to continue despite these departures from procedure. Plant director Viktor Bryukhanov's management culture and the Soviet program's demand for schedules had already delayed the test and now encouraged its completion. To avoid automatic interruptions that would abort the rundown measurement, operators overrode and bypassed several automatic protections and interlocks, and some emergency systems were taken offline or isolated. Subscribe. Apparently, that wasn't on the checklist. The net effect was a complex, fragile configuration. Most rods withdrawn, automatic shields dimmed, a xenon-drowned core, and an RBMK whose positive void coefficient would amplify any sudden steam formation. Every bit of procedure had been sacrificed to the test timetable, leaving the reactor in a precarious, gilded equilibrium where a single misstep could cascade into catastrophe. A taut, ominous momentum carrying Unit 4 toward the violent unraveling that Act 2 will confront. Seconds after a fragile, gilded equilibrium, the reactor betrayed its operators with a violent, sepia-tinged roar. A sudden, catastrophic power surge ripped through Reactor Unit 4 at about 1:23 a.m. on April 26, 1986. Operators hit the emergency shutdown, AZ-5, expecting to halt the runaway reaction. But the RBMK's fatal design quirks turned that hope into disaster. Graphite-tipped control rods displaced coolant as they entered the core and, together with a positive void coefficient, produced a massive spike in reactivity. That spike led to a steam explosion and a violent rupture that tore open the reactor vault and sent a graphite fire into the night. The blast ripped pressure tubes from their channels, exposing the hot graphite moderator to air and igniting a conflagration that burned for days, lofting a black metallic plume of radioactive debris skyward. The breach expelled huge quantities of radionuclides. Iodine-131, with an 8-day half-life, flooded the environment and posed an acute thyroid risk, especially to children. while cesium-137, with a roughly 30-year half-life, settled into soil and the food chain, promising long-term contamination across Ukraine, Belarus, and Western Russia. First responders arrived within minutes. Pripyat firefighters led by Lieutenant Vladimir Pravik, including Vasily Ignatenko, Nikolai Titanok, and Senior Officer Leonid Telyatnikov, climbed steel ladders and fought flames on the shattered roof, unknowingly bathing themselves in lethal gamma and beta radiation. Many of those firefighters, along with dozens of plant personnel who stayed at the scene, received doses high enough to cause acute radiation syndrome and were rushed to specialized care at Moscow's Hospital No. 6. Several would die within weeks. Helicopters began dropping sand, boron, lead, and clay in improvised attempts to smother the blaze and capture radioactive particles. But by then, the plume was already beginning its grim continental sweep. The explosion and the open burning core had turned a local experiment into an environmental catastrophe and set the stage for the evacuation, containment, and political fallout that Act 3 must confront. Radiation that had smoldered unseen through the night finally became undeniable when instruments outside the Soviet Union sounded the alarm. On April 28, 1986, technicians at the Forsmark nuclear plant in Sweden recorded anomalous gamma levels and traced the source back to Chernobyl, forcing Moscow to admit an accident. But in Pripyat, the human cost had already become painfully clear. Firefighters and plant staff who climbed onto the wreckage collapsed with nausea, burns, bleeding gums, and fever as acute radiation syndrome ravaged their bodies. Men like Vladimir Pravik and Vasily Ignatenko, already gravely exposed, were rushed to hospitals. Pravik died on May 11th and Ignatenko on May 13th. Despite these crimson warning signs, official caution lagged. For more than a day after the blast, many of Pripyat's roughly 49,000 residents lived in ignorance, with windows open, milk left on kitchen tables, and children playing in streets dusted by fallout. The evacuation order finally came at about 2 p.m. on April 27, 1986. A belated formal command that emptied the town into buses and military trucks with instructions to bring only essentials and the promise that the evacuation would be temporary. Pale, dazed families departed toward uncertain corridors while soldiers and specialists in protective gear arrived to impose a grim order on the landscape. The Soviet military, civil defense troops, and medical teams set up decontamination stations, field hospitals, and reception centers. Dosimeter teams mapped radiation gradients, and helicopters dropped sand, boron, and lead onto the exposed core. Still, the delay had widened the damage. About 116,000 people from the 30-kilometer zone were evacuated in the following weeks, and a 30-kilometer exclusion zone was declared as contamination, including iodine-131 and cesium-137, spread across Ukraine, Belarus, and into Western Russia. The toll mounted in two registers: the acute deaths and illnesses among first responders and plant workers, and the dawning realization that whole communities faced long exile and invisible contamination. That mounting, inexorable pressure, medical collapse, international alarm, mass displacement, tightened like a drawn wire toward the climactic struggle to seal the dead reactor and stop the plume. In the stunned streets of Pripyat, the response hardened into a grim brass and velvet campaign of containment. Helicopters began dropping tons of boron, sand, lead, and clay onto the exposed heart of Reactor Unit 4 in the hours after April 26, 1986. The drops were meant to smother fires and capture airborne radionuclides even as fallout sailed across Europe. Inside the wreck, a trio of engineers, Alexei Ananenko, Valery Bespalov, and Boris Baranov, descended into a flooded sub-basement to open valves and drain coolant, a desperate move that likely averted a secondary steam explosion. Thousands of soldiers, miners, firefighters, and plant workers were drafted into a sepia-toned, immediate army of liquidators to shovel radioactive graphite and debris from roofs, scrape contamination from streets, and load radioactive rubble by hand into burlap sacks. Boris Sherbina, who headed the government commission, and scientists including Valery Legasov, coordinated emergency engineering choices while teams worked around the clock. Between May and November 1986, engineers and thousands of construction crews raised the hastily designed concrete and steel sarcophagus over Unit 4, known as the shelter object. The brutal, decisive enclosure stopped the worst of the massive releases but entombed the core and left many workers heavily irradiated. The effort sealed a technical rupture, but also sealed human sacrifice into a radioactive shadow, resolving the immediate crisis while bequeathing a long, tragic legacy. Even after the sarcophagus sealed Unit 4, the firefighting and immediate response produced grim, long-term consequences. Medical follow-ups showed a sharp rise in thyroid cancer among people who were children when exposed in Ukraine, Belarus, and parts of Russia after 1986, linked to uptake of radioactive iodine-131. Long-lived cesium-137 contamination, with a roughly 30-year half-life, fouled soils, forests, and waterways, creating hotspots that persist decades later. A roughly 2,600 square kilometer exclusion zone around the plant still cordons off Pripyat and dozens of abandoned villages, and hundreds of thousands of people were displaced. The RBMK fleet was retrofitted. Control rods were redesigned, the positive void coefficient problem was mitigated, automatic protections were strengthened, and operating rules were tightened. Internationally, Chernobyl prompted stronger IAEA conventions, faster emergency notification mechanisms, and a cultural shift toward greater transparency in nuclear governance. The disaster amplified demands for openness in the Soviet Union and reshaped public trust. The catastrophe remains a lasting scar on policy, the environment, and human life, and it forces one question: what will we remember and what will we change?